This clip covers various aspects of analysis and how to use UML, Unified Modeling Language, to create diagrams that visualize the domain and the resulting software design. Near the end of the presentation, I'll also discuss domain modeling in more detail. We've previously talked about how to translate requirements and use cases into a software design. What kind of notation can we use to describe the various aspects of our designs? You perform an analysis to get to an abstract model of the domain of your problem. You have a bunch of requirements and use cases that you extracted from the customer, and you want to translate those to a technical specification that's used by developers. You need to simplify the complexities of reality, but still take into account all relevant data in the application. What is an abstract model? A map is a good example. The problem domain is navigation. You don't need to know where the bins are on a map or which kind of tiling is used on the sideway. You do need to know how the roads are connected and what they are called. Why do we model software at all? Software is highly complex, and after a certain point, it's no longer possible to have a grasp on all the details. You need abstractions. Operating systems, for example, have many million lines of code. And in the end, code is written for a machine to execute, not necessarily for a human to understand. So, how can we model software then? UML is a language with 14 different diagram types or dialects. The most commonly seen ones are class diagrams. There are also use case diagrams, activity diagrams, sequence diagrams, and many more. Whenever you work in design or development, you'll surely encounter UML at some stage. It's the de facto standard used in the industry. So let's spend some time and discover what the UML notation looks like. First, activity diagrams are useful to describe existing business processes. You use these diagrams to validate that you and the customer are in agreement on how the current business works. You use a few different constructs to describe an activity. Use black dots for initial and final states, rounded rectangles for the activities, normal rectangles for data, diamonds for choices, black bars for parallel activities, and arrows to connect everything. Here's an example of an activity diagram that describes processing an order. You can see that there are various activities such as receive order, send invoice, ship order, etc. There's also a choice. An order is either accepted or rejected. As you can see, diamonds are also used to merge arrows from various parts in the diagram. This happens just before the close order activity. You use activity diagrams in the business modeling phase to establish how the business processes currently work. One of the most commonly seen types of diagrams is the ubiquitous UML class diagram, which gives a high-level overview of a software system. A class diagram has boxes that represent classes containing attributes and methods, and various types of arrows that describe the relations between the classes. Depending on what you need, you can draw these diagrams at different levels of detail. Here's an example of a simple class with one attribute and one method. The class diagram is drawn on the right. You can use modifiers to indicate the visibility or accessibility of methods and attributes. A plus means the attribute is public, a minus means it's private, and a hash means that it's protected. Python doesn't have access modifiers, but that doesn't mean you shouldn't include them in your design. You may use Python only for a prototype, and the real application is developed in Java or C#, which do have access modifiers. Also, access modifiers help establish responsibilities. If we know an attribute is private, then it's clear that the class that the attribute is in is responsible for it. UML also has a couple of other modifiers. You can find more information about this in the UML documentation. You can use different levels of detail depending on the situation. In early sketches, just use the class name. In a full design, also include attributes, types, and methods. And if a class is abstract, then you write its name in italic. UML also allows specifying relations between objects. Here, objects A and B are connected somehow. But in what way? Can we be more specific? UML knows 4 different kinds of relations between objects: inheritance, dependency, aggregation, and composition. Inheritance refers to the class inheritance mechanism. So B is a subclass of A. B is derived from A, or A is the superclass of B. And you can see the UML diagram that corresponds to this on the right. Here is a simple example of the mapping from Python class inheritance to inheritance in a UML class diagram. And this is a more complicated inheritance hierarchy with 2 levels. Aircraft and road vehicle are subclasses of vehicle. These subclasses in turn have other subclasses. Helicopters and fighter jets are aircrafts. Trucks and motorbikes are road vehicles. You can read an aggregation as B is a part of A. An aggregation is written with a line and a diamond shape, as you can see on the right. For example, a list of songs is part of a playlist. So a playlist aggregates a list of songs. Association is a lot like aggregation, but it's slightly looser. When you're dealing with an association, and B is not necessarily a part of A, but A does have a B. For example, an order has a customer, but the customer is not part of the order. An example of this you can see in the diagram on the right. In terms of code, if you have an aggregation or association in both cases, class A will have an attribute of type B. But as I said, there is a subtle difference between them. Now, when should you use an attribute and when should you use an aggregation? The rule of thumb is to use attributes for primitive types and aggregations to describe the relation with other classes. Of course, you can deviate from this rule if it helps you clarify the concepts. Here's an example of aggregation. An airport has aircrafts, which are either helicopters or jets, and aircraft is an abstract class here. Pause the video now and try this exercise for yourself. Create a UML diagram of the following code. Composition is a special form of aggregation, where the contained object cannot really exist by itself. For example, you can imagine that if you have a class person, it may have a composition with address, since a standalone address is not used in your application. Composition is important in languages that do not have garbage collection, since you need to know who's responsible for cleaning up data that's no longer used. Here's another exercise for you. Pause the video and sketch class diagrams for the 2 cases here. The first case describes planes and engines, both of which are kind of standalone. And the second case is about racing bikes. So now I assume you have created these class diagrams, and let's look at those. So in the first case, if planes and engines are kind of standalone, because an engine can be detached from a plane and sent over to maintenance, then the relation between planes and engine is probably an aggregation. The racing bike example could be a good candidate for a composition. Probably you never have to deal with the rear derailleur individually. It's always part of the racing bike. And finally we have the dependency, which is the vaguest of the relations. B depends on A, or B uses A in some way. In the case of aggregation, we know exactly what it means. A dependency is more subtle. You generally use it if there is a relation, but it's not aggregation. For example, objects of class B create objects of type A, or methods in class B take arguments of type A. More generally, if you change class A and that possibly affects class B, then B depends on A. And of course, in a good design, you should minimize such dependencies. Associations can be directed using arrow types. Here, there are three different situations. The first situation shows that a person knows the company he works for. The second is that a company knows its employees. And in the final example, both person and company know about each other. You can also write numbers with an association to indicate cardinality. In this example, every A has 0 or 1 objects of type B, and every B has 3 objects of type A. This allows you to indicate things like a car has 4 wheels, or you may borrow at most 6 books from the library. You can add labels to associations to clarify the nature of the association. For example, a person works for a company. And finally, you don't need to include arrows in an association. This can either mean that we do not know the exact nature of the relation, or that both objects know about each other. We will work with the first definition, but it's best to avoid undirected associations if possible. UML is a great way to start sketching out ideas. Initially, just use boxes and lines and flesh out the design as you go along. Once you have a UML class diagram, you can easily translate that into code. But be careful, because you can create UML diagrams that are not possible in code. For example, what is the problem with this UML diagram? MacBook inherits from both Apple computer and laptop. Most languages forbid multiple inheritance. And what's the problem here? The customer has a getBooks method, but the library doesn't have any means to actually access these books. As you can see, it's important that necessary information is available. A class can access its own methods, public attributes and methods of another class, and protected and public methods and attributes in its superclass. Again, Python doesn't have these access modifiers. But you'll be working in teams that use programming languages that do, so you do need to take this into account. So this is always something you have to remember. You're writing these diagrams for the developers who need to translate this into code. There is no UML compiler that checks whether your design makes sense. You need to do that. Check for common errors. Verify that all use cases are possible with your design. Finally, write so-called sequence diagrams and check that they work with your design. What's a sequence diagram? It captures the dynamic control flow of your program. This is opposed to class diagrams that capture the static nature of the system, concepts and their relations. Class diagrams don't say anything about what happens when you actually run the code. Sequence diagrams do. A sequence diagram has a number of columns that represent objects. Arrows between these objects represent method calls. Boxes indicate an object's lifetime from creating them to destroying them, and finally time flows from the top to the bottom. Here's an example of such a sequence diagram. There are two objects, main and data. Main calls setData, then getData, and finally data calls the returnData method in main. You can also create a more complicated sequence diagram with multiple objects. This is a diagram that describes what happens when you retrieve a collection of shapes, sort them, and draw them onto the screen. There are many other types of diagrams in UML for modeling static and dynamic aspects of code. We covered the most used ones in this lecture. Let's go back to analysis and design for a bit. You've talked to all the stakeholders, you've written use cases, and you've agreed on a set of requirements. How do you write a great design? A requirement document is written in English, is understood by the customer, and aims to establish the requirements of a system. A design, on the other hand, is written in UML, should be understood by the developers, and indicates how to implement the system. The customer won't understand this design, so how do you bridge the gap? Before you draw the UML class diagrams, create a so-called domain model. A domain model describes the problem domain in an abstract way and captures the user point of view. You can use lightweight UML for this, class diagrams, but without methods. This models the real world and not software components. For example, a domain model may describe a store with an address and a name that has a number of items in its inventory. Why do we write domain models? They help you understand the world of the customer and where the new software system fits in. In general, the domain model is a first step towards defining the software system and the structure of the data in it. You write a domain model by talking to experts in the domain, identifying existing systems and solutions, and identifying common patterns in the design. This part will come later in the course. You can also use textual analysis. You should have a lot of text at this point, in the shape of requirements and use cases. You can use this text to identify parts of the domain. Nouns are generally good candidates for classes, and verbs are good candidates for associations. LARMAN has an example that shows you how to do this. Here's a use case from the convenience store that we've seen earlier. You can look at the use case and select the nouns. Some of these are probably going to be classes in the system. But note that these nouns are just starting points. Not all of them should be classes. Some of them may be attributes, some nouns may be synonyms of other nouns, and some nouns may not be useful at all. Should customer, checkout, system, and receipt be classes? Probably. And how about price, total, and description? I think it makes more sense to make these attributes. Items and goods refer to the same thing, so we won't need two separate classes for these. And we can go through the same process with the verbs. and then we can translate verbs into associations between the objects. As the last part of this video, let's look at a few common pitfalls you may encounter when you create a domain model. The first one is making attributes too complex and object specific. Here, the cashier has a cash register, but the register may very well be used by other objects. So to fix this, split them up and keep your attribute types relatively simple. In this example, the cashier can find the register because the register is stored under an ID or number somewhere. But it's better to use associations instead of such keys, since an association makes the relation between these two things explicit. Noun-verb analysis is simple to execute, but you have to keep in mind that natural language is imprecise. You probably get way more nouns than relevant classes. As an exercise for yourself, take a look at the following case study on elevators. Here's a brief overall description. We have two example use cases. This is the scenario where the person fetches the elevator, which goes to the floor where the person is. And here is another scenario where the person gets into the elevator and goes to the requested floor. As an exercise, can you write a domain model in UML for this case study? Use noun-verb analysis to extract the concepts. And second, can you create a sequence diagram for each of the two use cases? Once you've developed your domain model, you still need to validate it. Does it reflect reality? Is every scenario accurately described? Are there conflicts in the model? Can the model be interpreted in different ways? And finally, can it be technically implemented? Verify that the different diagrams you created all agree, that naming is consistent throughout the diagrams. Are there any double definitions or missing associations? In order to get a fully consistent model, you probably need to go back and forth a couple of times. This is the end about the video about UML and domain modeling. If you have any questions, post them in the Teams channel of this course. Thanks for watching, and catch you in the next one.